Hello everybody, welcome to selecting loudspeakers and amplifiers, part of our sound system design process. As we discussed in the last class, we can design really from either end of the sound system. We can start with the beginning, of course, with the source devices and microphones and other inputs to the system, which will then dictate what kind of mixer we will need, what frame size and all that jazz. But we also need to start working from the back of the sound system with the loudspeakers and amplifiers, because as soon as we determine what type and how many loudspeakers we need, that will dictate how many amplifiers we need to drive those loudspeakers. And depending on how many amplifiers we have, that will determine our signal routing and signal processing required for those amplifiers. For example, if there are various different zones, do they need to be equalized differently? Can we just split the signal, or do we need a distribution amplifier? So the number of different factors that will be dependent on how many amplifiers we have in the system, which of course are dictated by how many loudspeakers we have. So before we get too far, we do need to talk a bit about Crest Factor, because this will have a determining factor with how we choose our loudspeakers and amplifiers. So, what the heck is Crest Factor? Well, basically, it's the difference between the peak of your program audio signal and the average level. Take, for instance, this signal down here, the typical full range music. As you can see, based on the waveform, the average level that we hear as, okay, how loud is this? The average level is fairly low, but the transients are relatively strong in comparison with the average level. So there's a very big difference between the average level and the peak level of this particular audio signal. So it's not really compressed at all. So in this sense, there is a 20 dB crest factor. So there's 20 dB of a difference between that average signal level and the peak. So say between here and there, it's 20 dB difference. Moving up to the opposite end of the spectrum, a signal with a 0 dB crest factor, but with essentially no difference between the peak and the average, is a square wave. Because if you think of it, really it's on, like it's always on. There is no other signal there. There's no real average, because the average is the peak. It's always peaking out. So you can look at this as super compressed audio, because there's basically no difference between the average level and the peak. So here in this case, a square wave is a signal with a 0 dB crest factor. Moving down kind of in the middle, to look at a couple different signals with different crest factors. Here a sine wave, standard sine wave that we all know and love, has a crest factor of 3 dB. That's the difference between the average level of a sine wave and the peak level. AES pink noise, which is a special kind of pink noise, which is specially calibrated with a 6 dB crest factor signal. And then there's typical pink noise, which may be generated by a special tone generator or something like that that just says pink noise output. That'll generally be about 10 dB of a crest factor. But again, AES pink noise is a special kind of pink noise with a 6 dB crest factor between the peak and the average of that signal level. So that's just something to be aware of. Okay, so now that we know what crest factor is, now we can apply that during our 6-step process for determining loudspeaker and amplifier requirements for our sound system. So there are 6 steps. The first step is determining the sound pressure level criteria. And what that is, of course, is the sound pressure level that you need to deliver to your audience or to the seating area. Step 2 is determining the real dB/SPL target, and we'll talk about that when we get to step 2. It has to do with crest factor. Number 3, determine the dB/SPL loss due to distance. So of course, if you are 80 feet away from a sound source, you're going to have to figure out, okay, well, what's the dB/SPL loss due to distance, inverse square law, and whatnot. Step 4, determine the loudspeaker requirements. Step 5, choosing a loudspeaker that fits those requirements. And step 6, choosing an amplifier that meets the requirements for that loudspeaker. So let's take a deeper look at step 1, defining the target. So first what we need to do is figure out, okay, what kind of sound pressure level do we need and how far away is it? In this case it may be to the furthest seating area from a given loudspeaker. So for instance in Leedy Theater you're going to be talking about the last row of seats. And then we have to determine the dBSPL required at that location. So using an example, if a given location is 75 feet away and we need to deliver 95 dBSPL at that location, that's our goal. So let's say it's a really loud concert or whatnot. So step 1, defining the target, 75 feet away, and we need 95 dBSPL at that location, which is 75 feet away. So step 1 is complete. Step 2, defining the real target. And this is where we take into account crest factor. Because it's one thing to say, okay, we need 95 dBSPL at that location, but if you take a greater look at crest factor, we know that depending on the crest factor of that program material that we are using in our sound system that we're amplifying, it's going to sound at a certain level. So even though we might have, for example, very uncompressed music that may have transients that are 20 dB above the average level, we're going to hear that average level as the level of sound. So that 20 dB crest factor audio signal that we're running through our sound system, yeah, we can deliver 95 dBSPL at that location, but the average is 20 dB less than that. So what we're going to perceive as the audio level is really going to be 75. So if we want that average level to be 95 dBSPL at that location, then we also need to add in that crest factor as headroom to that sound system. So now our 95 dBSPL system, if we have a 20 dB crest factor, now that's going to be 115 dBSPL. Now in this case, we're going to use an example of heavily compressed music which has a approximately 6 dB crest factor. So we take 95 dBSPL from step 1, add our crest factor of our program material, and that will give us the real target that we really need to deliver 101 dBSPL at that 75 foot away location. Now this is because we're only really hearing the average, but we need to leave enough headroom for the crest factor of the program material that we're amplifying. And again, for the full range music, 20 dB crest factor, again that will give us that 115 dB SPL real target level of what our loudspeaker has to produce to accurately reproduce that signal, the average signal that we hear of 95 dB SPL, plus enough headroom for the crest factor of that program material. Step 3, taking into account distance loss. This should be a cakewalk for you guys by this point. Of course, defining the dBSPL loss due to distance is another 20 log equation. Now it's 20 log of the furthest distance divided by 3.28 feet. Well, why 3.28 feet? Well, that's because it's based on loudspeaker sensitivity specifications. And on just about all of them, I'm going to say about 99%, the 1 watt output at 1 meter, which is 3.28 feet, is going to be the rated sensitivity. So that 1 meter is really the output of that loudspeaker. So whenever you see sensitivity specifications, it's going to be 1 watt, 1 meter. So we want to figure out, okay, based on that 1 meter rating of what that loudspeaker can produce at 1 meter away, what's the loss once you get further away from that loudspeaker? So in this case, if we're talking about 75 feet away from that loudspeaker, our reference point is 1 meter away, which is 3.28. So our reference being the denominator and our test level, if you will, being the distance away on the numerator, we take 20 log of 75 feet divided by 3.28 feet. In this case, gives us a loss of approximately 27 dB. So again, just to review very, very quickly, we've defined the target in step 1. So we've defined that we want 95 dBSPL at 75 feet away. In step 2, we've taken into account our crest factor and figured out how much headroom we really need for that SPL that we want at that location. So in this case, talking about 95 dBSPL, if it's a 6 dB crest factor signal, we really need 101 dBSPL. Or with a 20 dB crest factor full range music signal, we're really going to need 115 dBSPL at that location, 75 feet away. So step 2 is, again, just a refinement of our target. Step 3, taking into account distance loss. We have to know how much we're losing due to distance from that original location of our loudspeaker. Now here's where we take into account all of those and start figuring out what does our loudspeaker need to do. So what do? We take the real target, which is taking into account crest factor, at that distance location. We need to add the amount of distance loss, and that gives us the amount that our loudspeaker must produce. So for example, if the real target after taking into account crest factor is 101 dBSPL, because we're using a 6 dB crest factor for this example, we're going to add in the 27 dB of loss that the system must overcome, because we have to compensate for that 27 dB of loss somehow. So our loudspeaker must get louder to overcome that 27 dB of distance loss. So really we're talking about a total level of 128 dBSPL that loudspeaker must produce in order to deliver our 95 dBSPL average signal level at 75 feet away. Because again, we get that from our heavily compressed music, which is 6 dB crest factor. We have a 95 dBSPL target. We have to factor in the 6 dB crest factor, so that gives us that 101 dBSPL. But we're losing 27 dB due to distance at 75 feet away. So really it's producing 101 dBSPL, and we have to overcome 27 dB of loss due to distance. So our loudspeaker has to produce 128 dB SPL from that loudspeaker to give us what we need at 75 feet away. For this step, we need to choose a loudspeaker that meets or exceeds our continuous dBSPL requirements. Now a lot of times spec sheets will give you this information outright, but sometimes they won't, or sometimes it might be, well, let's just say the marketing guys might have gotten to the spec sheets before the engineers. So you really have to check and see, alright, what is the actual level that I'm looking at? If this loudspeaker says it can handle 3,000 watts, alright, well, is that continuous or is it peak? And depending on whether it's peak or continuous, that'll really make a huge difference in terms of what that loudspeaker is capable of. So we want to look at how our loudspeaker was continuously rated. Is it rated at AES, pink noise, or sine wave continuous? And then based on that, that'll help us determine the maximum peak output level of that loudspeaker. So to determine the maximum peak dBSPL output of the loudspeaker based on AES pink noise, we're going to take the sensitivity rating of that loudspeaker plus 10 log of AES pink noise power rating in watts of that loudspeaker. So for instance, in this case, it's going to be the power rating of that loudspeaker. So if it says, this loudspeaker is rated at 1200 watts AES pink noise, great, okay, then that's that value that we're going to put in here. And then plus 6, and this is the AES pink noise crest factor. So for example, the sensitivity of the loudspeaker plus 10 log of the power rating, the AES power rating that is, in watts, plus 6, which is the pink noise crest factor for AES pink noise. Now if our loudspeaker was rated using a sine wave, it's going to be the sensitivity of that loudspeaker plus 10 log of the rated power based on a sine wave, again this will be in the specification sheet, plus 3, where 3, giving a little asterisk there, 3 equals the crest factor for a sine wave. So we have to be sure of how the loudspeaker was rated, so we plug in the right formulas to get the max peak output level. And again, a lot of this information may actually be on the spec sheet, but this is kind of a guarantee that you can help derive it in case it doesn't, or if it gives you confusing levels based on continuous levels, or was it rated some other way. So it's kind of a way of double checking the spec sheets. It gets a little complex here, but we'll break it down with an example of the JBL AM 6340/64. It's a tri-amplified system, so it has a separate low, mid, and high driver. In this case, we're just going to look at the low frequency driver because they tend to be the least sensitive. But when you're doing this for real, you're going to have to do this same calculation for the low frequency driver, the mid frequency driver, and the high frequency driver to make sure that in all frequency bands, low, mid, and high, the output capability of that loudspeaker is what you need it to be. So the low frequency, the mids, and the highs will all have to produce that same output level that you need at that given location. But first, let's run through here. So we need to choose a loudspeaker with a max output of at least 128 dB SPL, because again, that was our loudspeaker requirement in step 4. Or greater, of course. If you want even more headroom, great, pick something with at least 120 dB SPL. Now we're going to take a look at the JBL AM 6340. We look at the spec sheet, and the low frequency sensitivity at 1 watt 1 meter is 99 dB SPL. Okay. Then we look at the AES power rating, which is shown as 1200 watts. So it can handle 1200 watts AES pink noise. All right. Then we use the formula in the previous page. Using the AES formula, its max peak SPL is 99 plus 10 log of 1200 plus 6. So again, if we go back here, we use this formula, max peak SPL, sensitivity plus 10 log AES pink noise rating power level in watts plus 6. So that's where we get the numbers from the spec sheet, plug it into the equation, crunch the numbers, and we find that the low frequency driver's max peak SPL is 135 dB SPL. And again, they may already tell you this on the spec sheet, but this is just a way of deriving it. Now again, this is the max peak SPL level. Its average capable level is going to be -6, because 6 is the crest factor that they used in that test signal to determine its power handling capability. Now that we've chosen a loudspeaker that we've determined will fit the needs, we have to figure out how much amplification that loudspeaker needs. So how much power do you need to drive this loudspeaker? Well, what we do then is we're going to use dB watts because it's a little bit easier to calculate. So dB watts is decibels compared to 1 watt. So it's capital W there. So our power in dB watts is the total SPL criteria minus sensitivity. And that gives us how many dB watts that we need to power that loudspeaker. And note that the total SPL criteria includes crest factor and distance loss. So this is the loudspeaker requirement number from step 4. Just be careful that you don't take that number from anywhere else. If you plug in the wrong number, you'll get the wrong result. So in our example here, our total SPL criteria is, again, we want 95 dB SPL plus 6 dB crest factor for headroom, plus we have to overcome 27 dB of loss due to distance. Okay? So our loudspeaker sensitivity, in this case the low frequency driver, is 99 dB SPL 1 watt 1 meter. So we take our total SPL criteria minus sensitivity, and that gives us the power in dB watts. So it's a total of 128 minus 99 equals 29 dBW. Now, to derive power in watts from power in dBW, we use this formula of 10 to the power of power in dB watts divided by 10. That may look familiar. It's a similar equation to derive volts from dBu. But in this case, deriving watts from dBW is 10 to the power of the power in dBW divided by 10. So plugging in the numbers, power in watts equals 10 to the power of 29 divided by 10, which is 10 to the power of 2.9, which gives us an answer of 794. And we can round up and just choose an 800 watt amplifier. So now we're able to choose our loudspeaker, choose an amplifier based on our requirements, and so now an 800 watt amplifier will give us all the power we need to drive that loudspeaker to the level it needs to be to overcome the loss due to distance and give us our 95 dB SPL level where we need it, plus take into account the crest factor of the program material, and it gives us everything we need. So again, just to quickly review those steps, we determined the SPL criteria of 95 dB SPL. We determined the real SPL requirement by adding in the crest factor, so that gives us our headroom requirement, which was 6 dB. So our real SPL target is 101 dB SPL. Step 3, we took our loss due to distance by being 75 feet away, and it was approximately 27 dB of loss due to distance. And then we figured our loudspeaker requirements based on overcoming that loss due to distance and our real SPL target, which gives us a total of 128 dB SPL that the loudspeaker must produce at 1 meter away to give us that average level of 95 dB SPL at that 75 foot distance. Then we chose a loudspeaker by determining what its maximum output is, maximum continuous output based on its power rating. And again, depending on how the power rating is defined, will tell us what the actual peak output level of that loudspeaker is. And then we can also figure out what the average continuous output of that loudspeaker is. And so then based on that, we choose an amplifier to drive that loudspeaker as loud as we need using our total SPL criteria, my sensitivity. Plug in the numbers, do the calculations, and we have our answer in terms of what kind of amplifier we need. Now keep in mind too that when you're choosing an amplifier, this is 800 watts into the impedance load of that loudspeaker. So in this case, it's 800 watts for that low frequency driver of our JBL 6340. So we have to look at what the impedance is. I believe it's 8 ohms. So if it is 8 ohms, we have to make sure we have an amplifier that will produce 800 watts into an 8 ohm load. So we have to be sure that we're not looking at something that's specified as 800 watts into 4 ohms and then really only maybe 400 watts into 8 ohms, that sort of thing. So we just have to be careful of that. Alright, then in class we can discuss a factory paging system example, a restaurant example for a background music system, or an auditorium. And we'll go over some things in class, and hopefully this gives you a little bit of a head start. Try and think of any questions, and we'll answer them all in class when we see you on Thursday.